Hello, welcome back. This is question 2 of the drone practice exam. So let's go through it together. So the drone was repaired, right? It had a little whoopsie, it crashed before, and LED strips were installed along the 4 arms. So we have 4 branches of LEDs, and it's running off a 5-volt battery. Okay, so we're told the power output, so P for power output, of one of the LED strips, okay, so each branch, is 2 watts. By first stating the voltage across each LED strip, calculate the current through each LED strip. So this is a parallel circuit, and what can we say about the voltage across the branches of a parallel circuit? The voltages are the same, and so if 5 volts is supplied, there is 5 volts across each LED. Yeah. So it says by first stating the voltage across, so let's just write that, 5 volts across each LED. Okay, and now let's just compare that to a series circuit. If we had a 5-volt battery, and we had 4 LEDs connected in series now, that 5 volts is now split across each LED. So they would each get 5/4 of a volt. Assuming they had the same resistance. Cool, so just watch out for series versus parallel. Okay, then it asks us to calculate the current through each LED strip. So what do we know? We know the power and we know the voltage. So let's scroll on up to our formula sheet. Again, this bottom row, what does it do there? Especially the first 2 equations, right, relate to electrical circuits. So which equation incorporates power, voltage, and current? Definitely the first one, P equals IV. So let's just write that down. P equals IV, where P is the power output of a circuit component, and it is equal to the current, confusingly I is for current, times the voltage. Okay, and what are we looking for? We are trying to find the current. So let's rearrange for current. So we want current by itself, so we need to divide voltage across, P divided by V equals current. Right, and conventionally we write the unknown on the left, but I'm just, it's just swapping it. So current is power divided by voltage. And if you're like, I don't know how to rearrange, well, let's have a look at a formula triangle where P goes up top, IV at the bottom. Complete the triangle. You're looking for current, so you cover it up, and you're left with power over, right, over V. P over V. Great, now that we have our equation, let me just move it across. Oh, there we go. Got our equation. Let's substitute in what we know. Power is 2 watts. What about voltage? 5 volts. So 2/5. 2/5, what's that? 0.2, 0.4. And what are the units for current? Current are measured in amps or amperes. So capital A. And that is an achieved question. Alright, part B. Calculate the resistance of each LED using your answer to A. So we are now looking for resistance using our answer to A. Well, that was current, was 0.4 amps. So what relates current and resistance? So again, let's scroll right up. We're sticking to those two equations because we're looking at DC circuits. Ohm's law, V equals I times R, voltage equals current times resistance. So let's write that down. V equals IR. Great. And what are we solving for? Well, we're solving for resistance, which is over here, which means we need to divide I across. So resistance would be voltage divided by current. And as a formula triangle, you can do the exact same. Looking for resistance, we're left with voltage over current. Now what's the voltage across each LED? Well, we worked that out before, 5 volts, divided by the current, 0.4 amps. So 5 divided by 0.4 gives 12.5. And the units for resistance, capital Omega for ohms. If you forget that symbol, you can write ohms. But it's just the funny horseshoe. Of course, you remember that. Alright, and that is an achieved question. Part C, explain why the LEDs were not connected in a series configuration. So that's like we drew up here, just on the right. So why are they not connected in series? So let's go back to what we said before about the voltage. Remember, for parallel, the voltages across each LED was the same, but for series, it's split. So maybe these LEDs require a certain voltage, and they don't work when connected in series. So we could say series, or in a series circuit, the voltage splits across components, which may not be desirable, right? We don't really know the specifications of these LEDs, but if they needed 5 volts to work and we connected them in series, well, then they wouldn't work. Why else is a series circuit a bad idea? Well, if one of the LEDs blows, right, stops working, since there's only one pathway for current to flow, none of the other LEDs would work. So we could say if one LED stops working, all other LEDs would also stop working. Right, and this is because there is only one path for current to flow. Compared to a parallel circuit, where if one LED blew, for example this first one, if that stopped working, current obviously can't come down this branch, but it can still flow around the other branches, right? And so the LEDs would still work. And so this is a merit question if you got both points, or if you explain the second point very well. Alright, part D. So LEDs are much more efficient than incandescent bulbs. LEDs convert 60% of their energy to visible light. Calculate how much energy in total was lost to heat in 10 minutes of operation. Start by stating the total combined power output of all LED strips. Okay, so if it converts 60% of their energy to light, let's assume that 40%, right, that remaining 40% is lost to heat. Yeah, there might be some sound, but it would be very insignificant. Alright, so what's the power output of one LED? Right, we're told that it's 2 watts. So what's the power output of all 4? 2 times 4, so that would be 8 watts. So power total is 2 watts from one LED. There's 4 of them, giving us 8 watts. Okay. And now, if they're on for 10 minutes, what is their total energy consumption? Okay, so we've got power, we've got time. Have a look at the formula sheet. We're looking at the bottom right. Energy equals power times time. So let's write the formula. E equals PT. P is 8 watts and T is 10 minutes. Again, we need to convert this to seconds. So 10 minutes times 60 seconds gives 600 seconds. What's 8 times 6? That's 48, so 4,800. And what are the units for energy? Joules. Okay, have we answered the question? We've found the total power output and we've found the total energy that the LEDs would consume in 10 minutes. But it asked us to find the total energy that was lost to heat. And so 60% goes to light, 40% goes into heat. So our final step would be heat is equal to 40% of our total energy. So I'm just writing it out like in full, just to make it easier to read, but you can skip that step and jump straight to heat equals 40% times 4,800. And if your calculator doesn't have a percent button, we know 40% is 0.4 as a decimal. So 0.4 times 4,800 gives 1,920 joules. And that is an excellence question. You would get achieved if you found the correct power. You would get merit if you got the energy, the power energy, and maybe use the 60% instead of 40%. But if you got the correct final answer, you would get excellence. Alright, and lastly for this question, discuss why the carbon fiber arms the LEDs are attached to help ensure the LEDs don't overheat. Right, so the LEDs are attached to the drone's arms, and those arms are made from carbon fiber. And they've given us some hints. Describe what a thermal conductor is, and then explain how heat is transferred away from the LEDs to the surroundings. Okay, so let's start with the thermal conductor. Thermal conductor is, what is it? I mean, it conducts heat, right? A thermal conductor, as opposed to a electrical conductor. So it is a material. In this case, it's carbon fiber, but generally it's a material or a substance that quickly, right, or efficiently transfers heat, where heat is just energy. So we've got the description of a thermal conductor. Now let's link it back to this context. So the hot LEDs transfer heat to carbon fiber arms, and what heat mechanism is it? Is it conduction, radiation, convection? Since they're touching, right, they're making contact, it is through conduction. And since the carbon fiber is a thermal conductor, this happens quickly, right? Linking it back to our definition. So we'd say this happens quickly as the arms, the carbon fiber arms, are thermal conductors. Right, that's why we chose carbon fiber as opposed to wood, right? Because it wouldn't conduct the heat away effectively. Okay, but now the arms are hot, so what happens next? Well, I mean, it's a drone, and it's in the air. So the heat will transfer from the carbon fiber to the air just surrounding it, right? The layer of air touching it. And of course that air gets blown away, so it's constantly renewed with less hot air. So as a sentence, the hot arms transfer heat to the surrounding air again through conduction. And so it's just the layer of air touching the carbon fiber. Whew, that would be an excellent question. So just as a diagram, let's say we have one of the drone arms. Here's a beautiful motor over here. And we have LEDs on top. Yep. So if we just zoom into that, here's the LED, and then here is the arm, LED. As the LED gets hot, through conduction, it will transfer its heat energy into the arm. That heat energy then flows through the arm. I probably should have mentioned that in my thing, right? Since it's a thermal conductor, the heat can flow through the arm itself as well. So spread it out, and then it will transfer its heat energy to the air surrounding it. Like so. And if you're wondering why the heck does that even matter, well, if the LEDs overheat, right, they don't function properly. So that is an important consideration. Alright, next up we'll do question 3 in the next video. See you then.